Hello and welcome. We hear about averages all the time, right? The average salary, the average temperature, the average time it takes to get to work. But what if I told you that the average is really only half the story? Today, we're going to dive into the part that's often missing from the picture, variation. We're going to see why understanding the spread of data is one of the most powerful ideas in all of statistics. Okay, let's just jump right into this with a simple question. Picture this. You're at a theme park. You've got two awesome rides in front of you, and the signs for both say the average wait time is 40 minutes. Based on just that one number, they seem exactly the same. So, which line do you get into? It feels like a total coin toss, doesn't it?
But hang on, what if you had a little more information? This is where you see the truth hiding behind those averages. Line A is super consistent. You're going to wait 38, 40, or 42 minutes. It's predictable. Line B, on the other hand, is a complete gamble. Yeah, you might get lucky and be on in 5 minutes, or you could be stuck standing there for 75. Both lines average out to 40 minutes, but they are wildly different experiences. This, right here, is why we need a way to measure that spread.
And hey, don't just take my word for it. The source material for today's explainer states this directly. This isn't just some side topic we're covering. Understanding variation is the absolute core of thinking with data. It's really the key that unlocks the full story.
So, why does all this matter? Well, because making a good decision with data, whether it's picking a theme park ride or something much more important, isn't just about finding an average, it's about seeing the entire picture. And that's exactly what we're going to learn how to do today.
So, how do we actually start measuring this spread? Let's begin with the most intuitive, most straightforward tool we have in our kit, the range. It's a great place to start.
And the formula? It couldn't be simpler. You just find the highest value in your data, find the lowest value, and subtract the two. That's it. This gives you a really quick snapshot of the total spread from one end to the other.
Let's put this into practice with a real-world example from our source data, wait times for Space Mountain. Just take a look at these 11 different wait times. Can you spot the highest and the lowest values in there? Yep, the longest wait was 75 minutes and the shortest was just 20 minutes.
So we do the quick math. 75 minus 20 gives us a range of 55 minutes. This tells us that the total spread in the wait times they recorded, from the shortest to the longest, was almost a full hour.
But here's the catch. The range, as simple as it is kind of a blunt instrument. Its biggest weakness is that it only cares about two numbers, the absolute highest and the absolute lowest. It completely ignores how all the other data points are bunched up or spread out. Just one crazy outlier can totally blow up the range, giving you a pretty misleading picture of what's really going on.
To fix the problems we have with the range, we need a more sophisticated tool. And that brings us to the gold standard for measuring variation in statistics, the standard deviation.
So the official definition is that the standard deviation is a measure of how much data values tend to deviate away from the mean or the average. In stats, we use the letter S when we're talking about a sample of data, and we use the Greek letter sigma, when we have data for an entire population.
Okay, so what does that technical definition really mean in plain English? Just think of it like this. The standard deviation is the typical distance any single data point is from the average. A big standard deviation means your data's all over the place, like that risky theme park ride. A small one means the data is all clustered tightly around the average, like our predictable ride. And crucially, it's measured in the same units as our data, in this case, minutes, which makes it super easy to interpret.
Now, let me be clear, you are almost never going to calculate this by hand. Software does it instantly, but it's really helpful to understand the process. A computer first finds the average. Then it measures how far every single point is from that average. It squares those distances, averages them out in a special way by dividing by n-1, and then, finally, it takes the square root to get back to our original units.
So when we run our Space Mountain wait times through that process, what do we get? A standard deviation of 16.6 minutes. What that number tells us is that a typical wait time tends to be about 16.6 minutes away from the average wait time of 39.1 minutes, either higher or lower. You can see how that's a much richer piece of information than just the range.
Okay, so we have a number, 16.6. Great, but what can we actually do with it? This is where the magic really happens. Let's look at how we can use standard deviation to quickly make sense of our data.
The first tool is a fantastic little shortcut called the range rule of thumb. It basically says that for most data sets, the vast majority of your values, we're talking something like 95%, will fall within two standard deviations of the mean.
So you take the average, go 2 standard deviations up, 2 standard deviations down, and that little window should contain most of your data.
And this chart illustrates that idea perfectly. That yellow area in the middle, that's your normal or expected range of values. Anything that falls outside of that 2 standard deviation window, out there in the green zones, is considered statistically significant. It's an unusually high or an unusually low value that's probably worth a closer look.
Now, if we happen to know that our data has a specific shape, the classic symmetrical bell-shaped curve, we can get even more precise than that rule of thumb. For that special case, we use something called the empirical rule. This famous bell curve diagram tells us everything we need to know. For data with this shape, about 68% of all your values will be within 1 standard deviation of the mean. If you widen that out to 2 standard deviations, you've captured 95% of the data. And if you go all the way out to 3 standard deviations, you've accounted for pretty much everything, 99.7% of all data points.
So, the empirical rule is powerful, but it's a specialist. It only works for that nice bell-shaped data. What about all the other messy, real-world data shapes? Well, for that, there's a more general rule called Chebyshev's theorem. It's not as precise. It only guarantees that at least 75% of data is within 2 standard deviations. But its superpower is that it works for any dataset, no matter what it looks like.
All right, let's wrap this up with 2 final closely related concepts that are super important in the world of statistics: variance and notation.
You might also hear people talk about variance. Don't let the name scare you. It's very simple. It's just the standard deviation squared. If you remember our calculation steps, variance is just the number we had before we took that final square root. Its units are a little weird, like minutes squared, which is why we usually prefer talking about standard deviation. But variance is a really fundamental building block in more advanced statistics.
And finally, here's a quick reference guide for the symbols we've been talking about. Basically, we use regular Roman letters like S for samples, which are just a piece of the data. And we use Greek letters like sigma when we're talking about the entire population.
So we've come full circle. We started with 2 theme park rides that looked exactly the same because they had the same average wait time. But now we have the tools, range, standard deviation, variance, to see the whole story. The big takeaway here is that an average, all by itself, can be really misleading if you don't know its variation. So the next time you hear an average, I hope your first question will be, that's interesting, but what's the spread?